Well, good morning. Hey, it's Tuesday, 5/26/20. Almost thought it was Monday. It's the first day of the week after the holiday, but it's Tuesday. Can't believe it's the end of May. Can't believe our seniors are not with us. Maybe the seniors are going to watch this anyway and go with it. Today we're going to try to look at pendulums. All right, so I have a pendulum here. I think in your camera frame you can't see the hook on top of the wall, but it's up there. I got a string here that's, at least 1.5 meters long, maybe a little longer than that. And right now I have a 500-gram mass hanging on the end, and I wanted to investigate some properties of pendulum. So when a pendulum swings, it takes some time for it to go and make a cycle. Okay, now one cycle or one oscillation is the time that it takes before it starts repeating. So if I imagine starting there to there, it's the time to go across and back, and then it repeats that motion. Okay, I mean I could measure from here to there to here again. Okay, that amount of time is called a period, and is given the symbol capital T. So it's time with a big T. Okay, it is the time for one oscillation. It may seem kind of obvious that the period should depend on how big the swing is, right? I mean, if it's got a little tiny swing compared to a great big swing, I want to explore that though. So I have some marks up painted on my, or drawn on my board here. So I know this is 0 degrees, this is perpendicular, 5 degrees, 10, actually, no, this was 10, 20, and 30. So this is a 30-degree angle right here, and I'm going to let this go. And I have a stopwatch on my watch. I'm going to try to get myself synced. I'm going to start it right over here. I timed one oscillation. Now, in class, we would usually do at least 10 oscillations. I'm just trying to speed things along here a little bit. We'll see what I get. For one period of this pendulum, I came up with 2.38 seconds, and that was at 30 degrees. I think some of my screen is probably cut off here for you, so I'm going to do this again. At 30 degrees, 2.38 seconds. Okay? Well, let's try this at just 20 degrees. Okay, I'm going to get myself synced, and I'm going to start it right now. And 2.54. Okay. What if we try just 10 degrees? Next time. Yep. And 2.58. Let's get a couple others. Let's try, let's see, 10, 20, let's try 25 degrees. $2.58. Okay. Let's just try right here. Let's see, this is probably about 32 or 33 degrees, but I don't want to go any further because I got a ridge on the board. .54. So, all right, what I'm looking at here is, I had one kind of odd number there. You know what, I'm going to redo the 30. Go right here at 30, and get in sync. 2.66. So I don't think that that number right there reflects anything different. If you look at my data, to me, it's all really kind of clustered on the same place. It doesn't seem like the period depended at all on the amplitude of the swing. That may seem weird to you, but if you think about it, when I look at this, if I have this right over here, let's just say, okay, here's where my mass is. Hope you can see that. I'll go here. Here's where the mass is. Now, when it's at that point, we know that this is going towards the center of the circle. So the string is providing a centripetal force. We know that the weight of this is acting straight down. And so what there's going to be is along a tangent line to the circle, right? The circle would be whatever. Along the tangent line, there would be a component of the weight that's accelerating it. Now, if this is further down here, the weight's pulling down, the component force gets smaller. If this is further out here, the component gets bigger. So the force that's making it accelerate back towards the center is getting bigger as we get towards the outside. And of course, if it were right there, there's no force making it go to the sides because the weight is acting straight down. So what that means is when I have a smaller angle, I get a smaller force and therefore a smaller acceleration. So it moves, but it moves slower. And it takes the same amount of time to complete an oscillation as it does when it's out here. That's not real intuitive, but the data backs it up. Okay? All right, what else? This was all a 500 gram mass. I'm going to switch that out for a 100 gram mass. Now, there's a little problem here in that those masses aren't exactly the same length, and so the center mass might be slightly different, but I think it's probably close enough for us to see. And so let me try some of this again. I'm going to go 30 degrees and let it go. And 2.65. Let's try 20 degrees. .56. Let's try 10 degrees. 2.57. 25 degrees. Oh, didn't get it. 2.64. 32. That was what I had right over here. 2.69. Let's go back to 30 degrees. 2.64. All right, now when I look at that set of numbers compared to that set of numbers, I don't know that I see enough that I could call a considerable difference. I might want to, you know, on average, these average just slightly higher than these, but considering that we changed, this is 1/5, this is 20% the mass of the other object. And if there was any change in these numbers, it is incredibly minimal. In fact, I mentioned that there's a length thing here. That might be more possible, more reasonable, that it was a length thing. So here's what I'm going to do. I'm going to go back to my 500 gram mass, but I'm going to change the length. The way I do this is I coil up some of my extra string up top. All right. And so this was the 0.5 kilogram. This was a 0.2 kilogram. Now this is going to be back to 0.5 kilogram, but a different length. This is a shorter length. We'll see how that applies. So I'm going to go through the same series. 30 degrees. .39. And 20 degrees. I'll do it from this side here. Boom. 2.37. Okay, let's try 10 degrees. .35. 25 degrees. 2.28. All right, now I'm going to stop there because I can already see. When I changed the angle, I got essentially no change in my period, okay? When I changed the mass, it doesn't look like we got a change in the period. But when I changed the length, that looks like, I mean, I did have this one outlier over here, But those are all averaging around, 2.5 something, and these are now 2.3 something. There did seem to be a change when I adjust. So it seems like things that the period depends on, okay, period does not depend on the angle. Period seems like it does not depend on the mass. Period, it seems like it does depend on the length. Okay? Now, there's something else that I wish I could test with you. I wish we could take this to different planets. I wish we could test this on Earth and Mars and Mercury and Saturn, if there was a surface of Saturn, Jupiter, the Moon, Titan. Some of those aren't planets. Okay, gotcha. But I wish we could go to places where the gravity was different and see what happens. Because gravity is what's causing the weight here. Gravity is what's causing the force. So I wonder if that would make a difference. Well, when all is said and done, physics has come up with an equation for the period of a pendulum. The period of a pendulum is equal to 2 pi times the square root of L over G. 2 pi. This is tracing part of a circle, right? And pi is a big part of circles, right? It's the ratio of the circumference to the diameter. So it's maybe not unreasonable for pi to show up there. Pi shows up in an awful lot of places in our physical world. And this isn't necessarily obvious, but we did see that the period did vary with length. So here it is, there's length. And I suggested to you that maybe the period would suggest with the acceleration of gravity on different planets. And that's one that we can't test here, but, well, we could go to the top of a mountain and to, the bottom of Death Valley, and we could try little things, but you and I can't really test that. So here's the formula. Now, what I want you to do is practice a little bit of algebra quick. Can you rearrange that equation for the period of the pendulum? Can you rearrange this to find out what's the length? Okay, go to it. Step out of your way. Okay, so we're going to work from the outside in. Well, we got a radical in here, and I don't want to solve for my length under a radical. So let's square everything. So I'm going to square the t. I'm going to square the 2. I'm going to square the pi. I'm going to square the square root of L. I'm going to square the square root of G. Okay, now we got rid of our radical. We just squared everything. Okay, now let's get L by itself. So what I'm going to do is multiply both sides by G. I multiply here by G, then I multiply over here by G, then that's gone. Okay, so at this point, if I rewrite this, I've got G times T squared equals 4 pi squared L. So now to get L by itself, let's divide by 4 pi squared. Let's divide by 4 pi squared. L, the length of our pendulum, equals G T squared over 4 pi squared. All right. A little bit more. What if I wanted to find G from this formula? Well, honestly, it'd probably be a lot easier to find G from this formula or this formula that we had up here. Let's just go to that intermediate. G times T squared equals 4 pi squared. You can't see that. I'm sorry. Well, right here. From this, if G T squared equals 4 pi squared over L, then all we have to do is divide by T squared, divide by T squared, and you have an expression for G. Okay? So, you got some ways of rearranging this. All right, let's do one or two examples real quick here. What is the period of a 2.57 meter long pendulum on Earth? Okay, so I gave you a problem that you don't have to rearrange. So we have period is 2 pi square root of L over G. Okay, so 2 pi square root of 2.57 meters over 9.80 meters per second squared. Meters cross off, second squared comes to the top. Take it out of the radical, we're going to have seconds. And two times, oh, I know there's pi on here, so there's pi, times square root 2.57 over 9.80. I close the parentheses, it equals, and it tells me I have 3.22 seconds. Okay? That's a fairly long pendulum. Not as long as what Walter Lewin had in his lecture the other day, though. Okay? One more. Let's say if the period of a 2.57 meter long pendulum is 4.73 seconds, what is the value of G? Okay, so I'm going to take my equation. I'm looking for G, so I got to solve that. I'm going to square everything. T squared equals 4 pi squared L over G. And then I'm going to I want to get G out of that denominator, so I'm going to multiply by G, get rid of that. And then I'm going to divide by T squared to get rid of that. So there's my equation. I plug it in. 4 times pi times L was 2.57 meters divided by 4.73 seconds divided by 4.73 seconds. And look at my labels, meters per second squared. That's an acceleration. That's good news. And hopefully I'm not going off your screen. Let me take a peek. Oh yeah, we can still see that. 4 times pi times pi. Notice I put it in twice so I didn't forget to square it. Times 2.57 divided by 4.73 divided by 4.73 equals, and I got 4.53 meters per second squared. So I don't know where we are. Maybe we're at some point in space, well above the Earth. In fact, that's one of the ways that we try to determine altitude is by measuring the period of a pendulum. And if you know the period of pendulum, you can calculate your G value And from that, we can know how far we are off the surface of the Earth. So, all right, there's a couple samples. I'm going to be asking you to do just a couple problems to turn in.